Okay, why do we devote an entire chapter to water? It's a universal solvent. Why were they so excited when they found water on Mars? Life. Without water, you're not going to have life. So, as we know it. So, again, this is just a review of Chem 2. And so what we're going to do is talk about the molecule of water. Because when we talk about the intermolecular forces, these intermolecular forces play such an important role in our biochemical reactions and our interactions between the biomolecules. So we really need to pay attention. And we are going to make sure that everyone is on the same page with acids and bases. So there's no student left behind. So we're going to make sure that everyone is on the same page. Again, for those of you that have just had Chem 2, this is going to be a review. So it's a universal solvent. Again, because it's going to transport our chemicals. Just like going to the beach in the summer, it helps maintain a constant body temperature because it has a high what? Heat capacity. High heat capacity. Yes. I'm relying on my chemistry major to answer all these questions. Of course, it's part of our digestive fluids. And remember, I talked about the biotransformation dissolves our excretion products in order to get out of the cell. So what cell part does that? What did I say? Which organelle? The smoothie are. Yeah. Okay. All right. So the hybridization on our oxygen is sp3. You never thought I'd talk about hybridization in biochemistry, did I? Or did you? So why? Because we have 2 lone pairs and 2 bonding pairs. That's 4. That's an sp3 hybridization. Tetrahedral geometry. That makes the molecule bent. Now remember, lone pairs are fat and fluffy, and they take up more space than our bonding pairs. So normally in a tetrahedral, the angle is 109.5, but because these guys are fat, we are going to squeeze the 2 hydrogen bonds together, and so it's less than 109. So because of this geometry, it's not a linear molecule, but it's a tetrahedral shape for the electron pairs. Water is a polar molecule. What does that mean to be a polar molecule? That's right. One side is slightly positive, not positively charged. It's not ionic. Slightly positive, and one side is partially negative. You have to have polar bonds in order to have a polar molecule. So the polar bonds are the hydrogen and oxygen polar bonds. But if you look at the geometry, water could be nonpolar, right? You could have this, right? But that's not true. Okay, it's not straight. This is not true. It's because of the bent geometry. That is why water is polar. So in a polar bond, you have one atom that is more electronegative and one atom that is less electronegative. Which atom is the most electronegative atom? Fluorine. We don't have fluorine in biochemistry, thankfully. Hopefully not. So our nitrogens, our oxygens, sometimes our sulfurs, we call as our electronegative atoms. So the general trend is that it points to fluorine. The higher the electronegativity of our atom, the more it hogs those bonding pairs electrons. These numbers are made-up numbers. You can't measure these numbers. they're a rating system that Linus Pauling made up. Boy, what a scientist Linus Pauling was. He is the only scientist, I believe, to have won Nobel Prizes in both science and in peace. He got, for his protein determinations, structure of proteins, he got a Nobel Prize. He also got a Peace Prize for lobbying to stop above-ground nuclear testing. I think he passed away not too long ago. And the gentleman that wrote the general chemistry book that we use here had met him. So when he came to visit our campus, I was like, you met Linus Pauling. That is really cool. I just like to be in his presence because he had been in Linus Pauling's presence. So it's sort of like somebody that met, like, famous person that, you know, these are my rock stars. Like, I don't watch the Golden Globes or any of that because they're not rock stars to me. Linus Pauling, like, 2 Nobel Prizes. Then he went a little wacky in his old age.
Don't they all?
You're not saying anything about it. What happened is he started, you know, vitamin C and how people should take, like, large doses. He was nutty about vitamin C. And he went on this kick about, you know, you should have large doses of vitamin C to stay healthy. I think, you know, it's an important part, but it's not the whole thing. And he was, you know, he lost a lot of his respect, you know, people's respect because of his wackiness with vitamin C. But this guy he was in the race for the structure of DNA. He lost out. But he was in that race. He came up with this scorecard for electronegativity, and he won the Nobel Peace Prize. I mean, that is quite the life that I probably won't have. Anyway, so remember, oxygen in biochemistry is going to be the most electronegative. Nitrogen is also going to be electronegative, and these guys not so much. So you can't just have polar bonds. The bond between oxygen and hydrogen is a polar bond. But remember, you have to have geometry. So we have to have a net dipole moment in order to have a polar molecule. Now, dipole moment is something that is measurable. It's measured in Dubai's. And there's a typo on here. What is wrong on this slide? What is wrong on this slide? Yeah, the arrow is supposed to go the other side. So if you guys could correct that. The arrow is supposed to go the other side. So when you are drawing your molecules and you want to show the dipole moment, because it's a vector quantity, vector has both direction and magnitude, the head of the arrow goes towards the negative side. So this one is opposite. And it's probably because the textbook was written by biologists and not chemists. No, what I do is I go through and take things out of the textbook. I write these questions, but I take pictures. I don't draw these pictures. Yeah, I don't draw these pictures. No way. I pilfer from the internet and from we are given access to textbook images, so I take them from the textbook. Nothing's more annoying than having a lecture that is totally disconnected from your textbook. So I try to take things from the textbook so you're like, oh, I saw that. I do deviate quite a bit and jump around a little bit, but it's not going to be exact. But yeah, so they made a mistake here. I leave it in here because I like to point out their mistake. It makes me feel good. So, all right, so here, what it is we have really a dipole moment here going from hydrogen to oxygen, another one here, and they add together to go this way. So the head of the arrow is pointing to the oxygen. I don't care about these van der Waals and these bond lengths. I am never going to ask you about bond length. All right, so carbon dioxide also has 2 bonds to oxygens. But why is it not, or why is it polar? Is carbon dioxide polar? No. It's symmetric, right? So you have two equal and opposites. This is correct. Two equal and opposite vectors for dipole moment, and they cancel out. Remember your vector geometry? Yes.
What is that 2 for?
Because there's two partially positive because it's pulled from this way. I'm not so concerned about that. I'm just saying that it's pulled this way and pulled this way. And remember your vector geometry. Look, now we're pulling in like algebra stuff. We pull everything together in this class. I love it. So water is truly a unique molecule, mostly because of its ability to hydrogen bond. This property leads to a high boiling point and melting point compared to similar molecules. Hydrogen bonding is an intermolecular force. All right? Yes?
So for water, what would be the difference between boiling and melting?
Boiling, you're going from liquid to gas, right? And melting, you're going from solid to liquid. So that's what the difference is.
Oh, okay.
So hydrogen bonding, and this is what I say in my general chemistry classes, and it's kind of weird. The difference between a covalent bond and an intermolecular force is that a covalent bond, you need chemicals to break down. Your stomach acids, your saliva, the chemicals in your saliva will break down the covalent bonds. But the intermolecular forces you can break with your teeth. You chew ice. When you're chewing ice, you're breaking hydrogen bonds. I'd be really impressed if you could break a covalent bond with your teeth. That would be impressive. But, yeah. But hydrogen bonding is one of the strongest intermolecular forces. And because of that, we draw like little dashes where we see it. And it's the interaction between an electronegative atom, such as oxygen, and a hydrogen that's covalently bound to an electronegative atom. Now, what does that do to this hydrogen? When this hydrogen is covalently bound to this oxygen, look at that hydrogen. That lone pair, the bonding pair right here, where is it? Is it around that hydrogen? No, it's over here near the oxygen. So this is basically like a naked proton sitting out there. And then you have some lone pairs coming along. Those lone pairs are basically interacting with a naked proton. So that's a pretty strong interaction. So remember that our intermolecular forces hold our molecules together. Intermolecular, between molecules. You can break them with little force. So if you crack ice, you're breaking intermolecular forces. And remember, the more that you have, the higher the melting point and boiling point. So think about solid, they're right next to each other. Liquid, they can roll past each other. And gas, they don't even see each other. So going from solid, you have all the intermolecular forces that you can have put together. They're just stationary. They might vibrate in place, but they're stationary. Liquid, you have to break some because they're rolling past. In gas, you have to break all of them. So because of that hydrogen bonding, that's additional intermolecular force, you're going to see that it requires more energy to melt and boil. There are many different types of non-covalent attractions, or our intermolecular forces. And these attractions are either the attraction of positive to negative, partially positive to partially negative, or a combination of these. So the strongest one is our ionic interactions of positive to negative. Salt, right? A salt is any cation, which is positive ion, to any anion, which is a negative ion. Yes?
I've had like 4 teachers tell me covalent is stronger than ionic, and 4 tell me ionic is stronger than covalent.
Covalent is stronger than ionic. And I'm going to show you the data. Okay? The next one is where you take a positive and or negative and interact it with something that is partially positive or partially negative. Hydrogen bonding is then the next. Van der Waals are a collection of our dipole, dipole, dipole-induced dipole, and our hydrophobic interactions. And we can say this induced dipole is also called dispersion forces. So here, an example of ionic interactions would be table salt, right? Or any other salt, KCl. Ion dipole would be between a salt and water, NaCl and water. Hydrogen bonding, I would say water or any alcohol. Our van der Waals forces, our dipole would be between maybe our alcohols together or any other dipole. Our dipole-induced dipole, when we have an induced dipole, what you have is something that's non-polar, but when it comes towards something polar, the electrons get swished around. Our hydrophobic interactions we're going to talk about later, and our induced dipole we'll talk about later. But hydrophobic interactions happen between water and something that's non-polar. All right, so to put this together and to answer Golan's question about the strength of covalent and ionic bonds, let's take a look at our joules, kilojoules per mole, kilocalories. Let's look at the joules. Covalent bonds are very strong, greater than 210 kilojoules per mole, where ionic interactions are between 4 and 80. All right, so they are definitely weaker. All right, think about an ice crystal, or not an ice crystal, a salt crystal. You can take a chunk of salt and break it apart, and that you're breaking ionic interactions. Hydrogen bonds are then next, and our van der Waals are much weaker. Hydrophobic interactions, again, I'm going to talk about later. So how much time do I have left? 8 more minutes. I'm going to ask that you guys stay after I stop recording so that I can take attendance. Okay. So let's start with our ionic interactions. And what we're going to do is we're going to apply them, because I know that you guys have learned about these before. I'm going to apply them to our biomolecules. So when do we see ionic interactions? Again, they occur between actually charged atoms or groups. So you have to have an actual charge. It has to be positively charged or negatively charged. In proteins, what we have is ionic salt bridges. We have amino acid side chains that are either acidic or basic. And if it's acidic at neutral pH, it's going to be negatively charged. If it's basic at neutral pH, it's going to be positively charged. So here I'm showing the side chain of an acid amino acid, the R group, and here's the R group of a basic one. And if this protein is at neutral pH, then the acid will have donated its proton and the base will have accepted a proton. So the acid's going to be negatively charged and the base is going to be positively charged. So we call it a salt bridge. Salt bridges are very important in our protein interactions. What would happen if water were present around this? It would have donated the hydrogen to water, hydrogen ion to water, but wouldn't water surround the oxygens of water, the hydrogens of water surround the negative part? And wouldn't the negative part of water surround this positive? So where do you think we see the salt bridges in our structure of our protein? You see it in the interior or the exterior, these salt bridges? Interior. Because when these negatively charges are around water, or the positive charges are around water, they get hydrated. So here, pretend this negative charge, this chlorine, is that negative amino acid. Then the positive side of water is going to surround it with a shell of hydration. If you have the positive, say the positively charged basic amino acid, then the negative side of water is going to surround it. This is what happens when you dissolve salt in water. Okay? The salt crystal dissolves. And why it dissolves is that it's more stable to have the sodium surrounded by the negative side of water and the chlorine surrounded by the positive side of water. Do you have a question? Go on.
Yeah, so these salt bridges are going to form inside the water.
Yes. The salt bridges are going to form in the interior of our protein. So say this is a negative acidic side chain, and this is a positive basic one. What they're going to do, and my whole body is the amino acid chain, they're going to fold up so that they're away from water and they can interact together inside. I love protein structure. Again, hydrogen bonding is weaker. We see hydrogen bonding when we have hydrogen covalently bound to what?
Fluorine.
Oxygen, fluorine. We don't see fluorine. Oxygen or nitrogen, basically. And then it's going to interact with a lone pair. And so what we see with water is that it can have 4 hydrogen bonds. That's a lot for one molecule. That's a lot of hydrogen bonds for one molecule. And what happens is remember, when you're a solid, you have the most intermolecular forces you can possibly have. So when you get 4 hydrogen bonds per water molecule, you get this 6-membered ring that looks like this. And it forms our ice crystal. What's in the middle? Nothing. Empty space. Nothing. And so what happens is when you go from liquid water to solid water, you actually create more empty space. And that is why the solid water floats on top of liquid water. You would think that the density of ice should be greater than that of liquid water, right? But it floats. So that's because of this 6-membered ring. And so because of all that hydrogen bonding, you have a really interesting thing that happens with the density of water, and it affects, of course, the melting point.